I'm Anil Kumar. Let me thank all my subscribers and viewers for watching my videos, writing comments and posting questions. Now this is the time when we are doing review of the unit on trigonometric identities. All the concepts which we have learned about correlated identities, CoFunction identities, compound angle and double angle will be reviewed in this particular video. So I'll kind of summarize them for you. Correlated identities, as you learn, were the identities where we are going to compare a triangle which is placed in quadrant 1, for example, and this angle, we'll call it alpha, or I'll treat this as x as an acute angle. We really want to relate all the angles here with that acute angle. So how can we do it? So we look into triangles which are kind of like this. Do you see that? So all these triangles, their orientation is almost similar. They're only reflected on x-axis or y-axis. So here, where we have reflection on x-axis or on y-axis, you may get triangles shown here. These are related and we call them correlated. Right, so I'll get back to identities term also. So what you notice here is that the triangle which we are talking about kind of remains same. We only worry about the quadrant. This is quadrant 1, quadrant 2, quadrant 3, and that is quadrant 4. And in each quadrant, you know, in the first quadrant, all are positive. So let me write A here, saying that all are positive. In second quadrant, sine is positive. In third, tan is positive. And in fourth, cosine is positive. So based on in which quadrant the triangle is, correlated identities can be remembered. Like this. For example, if you have sine pi minus x, then sine pi minus x is in which quadrant? It is in quadrant 2. So that is the quadrant, right? So second quadrant, let me write. Now in second quadrant, it is positive. And therefore, sine remains sine, but it becomes positive sine x. So that is the relation. Do you see that? But if I do sine x plus pi, or pi plus x, then we'll end up in quadrant 3. So we are in third quadrant, right? Now here, sine is negative, and therefore this is equal to negative sine x. So that helps us to remember all kinds of relations. We could also have, let me take one more example here. We could have, for example, tan 2 pi minus x. If I'm talking about tan 2 pi minus x, we're looking at this triangle which is in the fourth quadrant, right? Here tan is negative. And if you compare with x, which is in quadrant 1, always positive, in that case, we have to put a negative sign here, right? So we get negative tan x. Is it okay? So if you're in quadrant 4, tan is negative. So you get this. Perfect. So these are all correlated identities. Now, when we say CoFunction identities, then what are we looking at? In CoFunction identities, we are looking for something like this. We again have a triangle, let's say with an acute angle of x. Okay, that is the triangle. But now here, the rotation is 90 plus or minus x. So it becomes kind of like this. So as you can see, the triangle orientation has changed Sine becomes cos, cos becomes sine, right? So now we are talking about triangles which are kind of like this. Do you see these triangles? So all four of them which I have drawn here we are looking at rotation. So the rotation could be pi by 2 plus minus x, or it could be 3 pi by 2 plus minus x, right? You could also think this as kind of like this. If I have a triangle here with an angle x here, in that case, the sides, let's say A and B, let's say ABC. When I rotate this triangle in this fashion, sides interchange, or we are looking from the other side. So what is this angle? This angle here is pi by 2 minus x for any right angle triangle. So in such cases, what really happens is we are now working on CoFunction. So in such cases, sine gets converted to cosine, tan gets converted to cotangent, cos gets converted to sine, right? So that is what it is. So basically, when you're talking about CoFunction identities, let me write down here, these are CoFunction identities. In that case, if you have something like sine pi by 2 minus x, for example, then we are looking into this triangle. This is x, right? This is x. So pi by 2 minus x is that angle. This is pi by 2 minus x. So here sine becomes cos. So that is equal to cos of x. So these are correlated, sine with cos. Do you get an idea? If I write cos 3 pi by 2, let's say minus x, we're looking into this quadrant. That angle here is 3 pi by 2 minus x, correct? That is 3 pi by 2, right? So since you are in quadrant 3, cosine is negative, we have to write negative sine. And since the orientation has changed kind of like this, you're looking from the other side. Cos becomes sine, so we get sine x. Perfect. If I have tan, let us say pi by 2 plus x, we land up in quadrant 2. So this one is in quadrant 2, correct? Here tan is negative, right? Only sine is positive. So it is negative, and the cofunction for tan is cotangent, so we get cot x. You see how it is done? So in the first case, our quadrant was 1, pi by 2 minus x. In the second case, it was quadrant 3. In first quadrant, all are positive, so it is positive. In quadrant 3, cos is negative, so we get negative result. In quadrant 2, tan is negative, we get negative result. So I hope the concept of cofunction and correlated identity is quite clear here. Now, based on this, we'll have some examples, and then I'll discuss compound angle and double angle identities. Okay, so we have done this concept in the previous page. Let me summarize it here. Okay, so we're looking into two types of triangles here, rather translations. One, let's take a triangle in quadrant 1 where the acute angle is x. We'll compare this triangle with the rotations. With these are circular functions. We are looking for these rotations. So, and we know that here all are positive. Sine is positive, tan is positive, cos is positive. So these are, we call them as correlated identities, which you could summarize as, let me write for sine first. So if I take this triangle, we are saying this is pi, so therefore, and that angle is x, so what is sine pi minus x? Since you are in quadrant 2, where sine is positive, it has to be positive. Sine remains sine. We have sine x. However, if I do sine pi plus x, you'll end up in quadrant 3, where sine is negative. So this becomes minus sine x. And if I do sine 2 pi minus x, we are in quadrant 3, where again sine is negative. So it is negative sine x. Do you get an idea? Likewise, you can write all your identities. Let me write few for tan. So if I have tan, let's say 2 pi minus x, again we are in quadrant 4, right? We are in quadrant 4, where tan is negative, so it is negative tan x, correct? However, if I write cos 2 pi minus x, in quadrant 4 cos is positive, so that will remain positive cos x. Do you get an idea? So these are the cofunction identities which we learned. And now let me say what are these are correlated identities. So these are the correlated identities which we learned. Now let's look into cofunction. Cofunction is when sine changes to cosine. So if this was our triangle, we do a rotation so that it becomes kind of like this. Now let me show you all 4 after rotation. So we may get situation, where the triangles are kind of like this. So if that angle is x, this angle which I've shown here is pi by 2 minus x. So when we are looking into pi by 2 minus x, then what we are seeing here is, if this is x, for example, that one is pi by 2 minus x, we see that opposite and adjacent signs interchange, and therefore we could write cos of pi by 2 minus x as cofunction of cos is sine, right? So it becomes, we write plus because we are in quadrant 1, all are positive, so it is sine of x. However, if I do cos of pi by 2 plus x, we are in quadrant 2. This angle is plus x on pi by 2, right? So here, since cos is negative, we get negative here and sine x. Got it? So if I do tan 3 pi by 2 minus x, we are in quadrant 3, where tan is positive. So we'll write this as positive cotangent x. But if I do tan 3 pi by 2 plus x, we'll end up in quadrant 4, where tan is negative. So it becomes cotangent x. Do you get an idea? So that is the kind of summary, and based on this, let's take up identities now. So we'll solve, or rather we'll simplify this particular expression before moving into identities. We need to simplify sine pi plus x plus cos pi by 2 minus x plus tan pi by 2 plus x plus tan 3 pi by 2 minus x. I would like you to pause the video at this stage, simplify this expression, and then look into my suggestions. So we have learned the concepts of correlated and cofunction identities. We'll take up this expression and simplify. We have sine pi plus x, cos pi by 2 minus x, tan pi by 2 plus x, and tan 3 pi by 2 minus x. So let's look into these in details. We'll compare all with our triangle in quadrant 1, where the acute angle is x for us. When I say sine pi plus x, it really means what? It means that there is a rotation, and pi plus x means this is pi, right? And plus x means you go further down and you form this triangle. So that becomes sine pi plus x. Now you are in quadrant 3, correct? You know the rule, all are positive here. Sine is positive in quadrant 2, tan in 3, and cosine in 4. So now in this particular case, tell me, what is sine pi plus x equal to? It is a similar triangle, but in quadrant 3, where sine is negative. and therefore it is minus sine x. Is that clear? Now let's look into the second one, which is cos of pi by 2 minus x. Now for pi by 2 minus x, I'll actually make another triangle here just to show you. Those are the cofunctions, right? So this is my triangle where the related angle is x. When I do pi by 2 minus x, that is pi by 2, correct? Minus x means you are on this side, so the triangle kind of becomes like this. Do you get an idea? So now the angle here, that is the principal angle, is pi by 2 minus x. You can see clearly that cos has become sine, but since you are in quadrant 1, it will be sine of x. Perfect. So this term becomes sine of x. Now let's take the next term, which is tan pi by 2 minus x. Now that is also a cofunction. Whenever you have pi by 2 or 3 pi by 2 involved, we are looking into cofunctions. So let me sketch this one again for you. Well, pi by 2 minus x, I'm sorry, this is plus x. Okay, tan is plus x, that's better. So pi by 2 plus x means we are in quadrant 2, right? This is pi by 2, so we add x to it. So what happens really is that we are now looking into this triangle. Now in quadrant 2, only sine is positive, tan is negative, so we write negative. And since the orientation changes, it becomes cotangent, right? Cot x. The last one here is tan 3 pi by 2 minus x. Now 3 pi by 2 minus x really means that you are in quadrant 3. This is 3 pi by 2, right? Minus x means minus x. Do you see that? So you are now looking into this triangle. So now the angle here is 3 pi by 2 minus x. Is that clear? You are in which quadrant? 3. In quadrant 3, tan is positive, so we'll write positive, and cotangent is the cofunction, right? We know all these four now, correct? So you can rewrite your expression. Sine pi plus x is minus sine x. Let me write here itself, minus sine x. Cos pi by 2 minus x is plus sine x. Okay. Tan pi by 2 plus x is minus cotangent x. And tan 3 pi by 2 minus x is plus cot x. Well, minus sine x plus sine x is 0. Minus cot x plus cot x is 0. So we get 0 as our result. But the idea here is again to consolidate the learning. How these correlated and cofunction are related, right? So now based on this we'll have an identity also. Rather we have two here. So the two questions here are based on cofunction identities. Tan pi by 2 minus x minus cot 3 pi by 2 minus x plus tan 2 pi minus x minus cot pi minus x equals 2. 4 minus 2 secant square x over tan x. That's the first one. The second one here is sin x equals to 1 minus 2 sine square pi by 4 minus pi by 2. Okay, before getting into the identities, let me complete the first one here. This involves cofunction identity. Then we'll get back to the second one, which involves double angle. Okay, so continuing with cofunction, let me move on and take up the identity relating to cofunction and correlated angles. So let's begin with the left side. On the left side we have tan pi by 2 minus x minus cot 3 pi by 2 minus x plus tan 2 pi minus x minus cot pi minus x, correct? Now when I say tan pi by 2 minus x, we mean that we are in quadrant 1, right? So we are in quadrant 1 for this one. In quadrant 1, all are positive. So this is positive. CoFunction, so it becomes cot. Clear? Now the second one, 3 pi by 2 minus x means we are in quadrant 3, correct? Here, cot and tan are positive, right? Cot and tan are positive, correct? So let me write down the rule here. All are positive, sine, tan and cos. Since all are positive, this negative is for that negative. We get positive tan x. Third one here is 2 pi minus x, means 2 pi minus x means you are here, correct? Quadrant 4. In quadrant 4, tan is negative, and therefore that changes to negative. Let me clearly write negative. This is a related angle. Orientation is similar, so it is tan of x. The last one here is cotangent pi minus x. That is, pi minus x means you are in this quadrant, right? This is pi minus x. Again, for cotangent, we are in quadrant 2, which makes it negative. And therefore, we have negative, let me write negative inside, cot x. Perfect. Is that clear? Now let me just add a step here to take care of these signs. We get cot x plus cot x, and I'm rearranging, right? Cot x plus, or let me just write as such. Plus and minus is negative tan x, minus tan x, minus minus plus cot x. So we'll combine these two. So we get 2 cotangent x minus 2 tan x. Now, cot x could be written as 1 over tan x, correct? Minus 2 tan x. And that could be written as, we could take tan x as common denominator. So we get 2 minus 2 tan square x. And let me take it on this side to further continue. We know 1 plus tan square x is equals to secant square x, correct? So for tan square x, we could write secant square x minus 1. So tan square x is secant square x minus 1. So that is what I hope you remember. So we'll replace this tan with secant square x minus 1. So getting back to this place now, what we get here is equal to 2 minus 2 secant square x minus 1. In the denominator we have tan x. That gives you 2 minus. Now, we had 2 here. So 2 times 2. Okay, so let's open this bracket. So 2 minus 2 secant square x minus minus becomes plus 2 over tan x. Okay, we want to, okay, so combine these 2's and we get 4 minus 2 secant square x divided by tan x, which is the same as the right side. Is it okay? So we have proven this particular identity. The key here was to understand CoFunction and correlated, and I hope the first part where we spent so much of time helps to do these identities. Let's move on and take the second example, which is based on a double angle. So here I'll just take a minute to remind you of this double angle formula. We'll work on cos A plus B, which you know is cos A cos B minus sin A sin B, right? And if I write cos 2A, that is to say, if I substitute B equals to A, then it becomes A plus A as 2A, and what we get here is cos A minus sin A, which is cos square A minus sine square A, and the double angle, right, cos 2A. However, we want to relate it to sine square, so we change this formula's form. I just wrote it like this again. Okay, so we'll use this equation and we'll replace cos square A as 1 minus sine square A. Then what you get here is 1 minus 2 sine square A, right? So what we see that we have a formula relating double angle. Cos 2A is 1 minus 2 sine square A. Perfect. Now here we already have 1 minus 2 sine square A. Do you see that? So let's look into the question now. Okay. The right side here is 1 minus 2 sine square pi by 4 minus x by 2. So treat this as A. In that case, I could write this as equal to cos of 2 times A. So this is cos of 2 times pi by 4 minus x by 2. Is that clear? So basically, I have substituted or related this formula. Is it okay? Now if you open the bracket, you get cos of, when you multiply, you get pi by 2 minus x. And from CoFunction identities, you have learned that now we're talking about relating this angle x with pi by 2 minus x, which is this triangle. Do you see that? So we are relating x with this, which is pi by 2 minus x. So it becomes sine x, which is the left side. So we have shown left side equals to right side. Okay, so that is how it could be done very easily. So I hope that's absolutely clear, right? Now let us take up the compound angle equations and try to see how to solve trigonometric identities involving with compound angles. So I'll take this up in part 2 of my video. So in part 1, we have discussed about correlated identities and CoFunction identities. And we took up 2 examples, which are these 2 examples, to really consolidate our earnings. Now in part 2, we are going to take up double angle identities. I hope that helps. Feel free to write your comments, share your views, and if you like and subscribe my videos, that'd be great. Thanks for watching and all the best.